In my earlier video, I had seen what is the eigenvalue and eigenvector of linear operator. Just recall, I had seen if T be a linear operator and where V be a vector space, and this is not only for linear operator, this is for all mapping. Here I have considered as a linear operator. That means I have considered the mapping from vector space to vector space. Then if and vector small v where v not equal to 0 is called eigenvalue. If Tv equal to lambda v for some scalar lambda, then the scalar lambda is an eigenvalue of the linear transformation T, and the non-zero vector is eigenvector corresponding to this lambda. Are you getting the meaning? OA. And today's goal of this lecture is characteristic polynomial. Actually, characteristic polynomial is very important for higher study. By characteristic polynomial and the idea of eigenvector and eigenvalue, you will see what is the fundamental theorem of algebra. Then I will say by characteristic polynomial Cayley-Hamilton theorem. Our next goal, I will see some example of eigenvalue and eigenvector of linear operator. Today I will say not only some example. In my earlier video, I had discussed what is the reflection matrix, what is the rotation matrix, and what is the projection matrix. And today I will see what is the eigenvalue and eigenvector of rotation matrix, precision matrix, and projection matrix. Okay? OL. Also, just recall, in my earlier video, I had discussed how we will find eigenvalue and eigenvectors of an linear operator. We had seen in my previous video, just recall. Choose a basis B for this V. Then find the matrix representation with respect to B. Then obviously, since this operator dimension of this vector space is n, so obviously this matrix representation would be n cross n matrix. Then AV equal to lambda V, because here I have given one matrix. So here the linear transformation as a matrix. Where V not equal to 0, then lambda is eigenvalue of A and V is eigenvector of A. We will find eigenvector as A. Since lambda is an eigenvalue of A, that means obviously there exists non-zero V in Rn with the condition AV equal to lambda times V. That means that imply A minus lambda in V equal to 0 vector, where for all V not equal to 0. That means A minus lambda in V equal to 0 vector means non-zero solution of the null space of A minus lambda n. Since non-zero solution of null space of A minus lambda n, that means obviously null space of A minus lambda n greater than equal to 1. That means since dimension of A minus lambda n always n, that means here the matrix as A minus lambda I. Now apply rank nullity theorem. Rank of A minus lambda I plus nullity of A minus lambda I equal to n. Then that imply rank of A minus lambda I equal to n minus nullity of A minus lambda I. And since nullity of A minus lambda I greater than equal to 1, That means rank of A minus lambda I less than equal to n minus 1. And since rank of A minus lambda I less than equal to n minus 1, that means obviously determinant of A minus lambda I n obviously equal to 0, because here rank not n less than equal to n minus 1. So that implies A minus lambda I n is not invertible. This concept I had seen in my earlier video. Okay, and I had seen if A be n cross n matrix over the field, then lambda belongs to F is an eigenvalue of the matrix A if and only if determinant of lambda I n minus A equal to 0. And this equation is called characteristic polynomial. And actually the eigenvector of A corresponding to lambda precisely the non-zero element of this null space of lambda I n minus A. Okay? That means the root of any characteristic polynomial is called as a eigenvalue. So from characteristic polynomial I will always get an eigenvalue. Also from eigenvalue I will get always a equation of characteristic polynomial. That means the set of eigenvalue and root of characteristic polynomial are actually the same. Now I will see what is the idea of characteristic polynomial. This is actually determinant of A minus lambda I equal to 0. And since I have considered A be n cross n matrix, that means this is the n cross n matrix minus lambda I means identity matrix equal to 0. That means that imply determinant of A11 minus lambda A12 up to A1n, A21, A22 minus lambda up to A2n, and this would be continue, and nth row would be N1, An2 up to Nn minus lambda equal to 0. This determinant actually would be an polynomial of degree n. This is equal to minus 1 to the power n lambda to the power n minus c1 lambda to the power n minus 1 plus c2 lambda to the power n minus 2, and this would be continue, and n term would be minus 1 to the power n cn equal to 0. And this equation is called characteristic polynomial. Okay? And solving this equation, I will get eigenvalue of this matrix. Are you getting the idea of characteristic polynomial? Well, now I will say characteristic polynomial of a 2 cross 2 matrix. Consider an arbitrary matrix A, B, C, D, where det of A equal to AD minus BC and trace of A equal to A plus D. Then I will prove the characteristic polynomial of A is lambda square minus trace of A times lambda plus det of A. Actually, my goal is I will prove this characteristic polynomial. And this is as, recall the definition of characteristic polynomial. We all of us know definition of characteristic polynomial as P lambda equal to det of A minus lambda I, which is actually det of ABCD minus lambda times identity means 1001, which is equal to A minus lambda B C D minus lambda. Therefore, this is actually equal to A minus lambda times D minus lambda minus BC, which is equal to AD minus A lambda minus D lambda plus lambda square minus BC. And from this line, we can tell lambda square minus a plus d lambda plus ad minus bc. And notice the equation. Here a plus d mean trace of the matrix. That means this is lambda square minus lambda times trace of a. And here AD minus BC means determinant of the matrix. So this is actually determinant of A. That means characteristic polynomial P lambda equal to lambda square minus lambda times trace of A plus determinant of A. And this is actually the characteristic polynomial of 2 cross 2 matrix. Are you getting how we have to find the characteristic polynomial? By determinant of A lambda I. This is the characteristic polynomial and the result would be such type. And the generalization of characteristic polynomial, when I will use n cross n matrix, then the generalization of characteristic polynomial, which is denoted as P lambda, would be minus 1 to the power n times lambda to the power n minus trace of A lambda to the power n minus 1 plus this would be continue plus minus 1 to the power n times data of A. This is the generalization of characteristic polynomial. And this calculation would be such type. And by this calculation we can easily find eigenvalue and eigenvector of characteristic polynomial. Are you getting? Oh, yeah. That means actually the characteristic polynomial would be such type AB n cross n matrix. That means characteristic polynomial means determinant of A minus lambda I equal to 0. And which would be just denoted as P lambda, which would be lambda to the power n minus C1 lambda to the power n minus 1 plus C2 lambda to the power n minus 2 up to this would be continue minus 1 to the power n Cn. Where Cn equal to determinant of A, C1 equal to trace of A. Are you getting this? Actual the idea of the characteristic polynomial. And degree of this characteristic polynomial would be depends on the matrix. Since here AB n cross n matrix, the degree of characteristic polynomial always would be n. Are you getting? And root of this characteristic equation are called as a eigenvalues. From this idea, root of the characteristic equation, I will see one nice theorem of algebra, fundamental theorem of algebra, which states any polynomial of degree n with complex coefficient has exactly n zeros. Counting multiplicity. And counting multiplicity means how many eigenvalue exist. Here n zeros means obviously root of this characteristic equation. Because characteristic equation is means data of A minus lambda I, and if for n cross n matrix there exists lambda 1, lambda 2 up to lambda n eigenvalues, which is actually root of this characteristic polynomial with multiplicity 1, then we can write P lambda as lambda minus lambda 1 times lambda minus lambda 2 times lambda minus lambda n. Are you getting? This is actually fundamental theorem of linear algebra. And this theorem is actually very important for any competitive exam. And not only competitive exam, for higher study of mathematics, all mathematics depends on this theorem, fundamental theorem of algebra. Now I will see one new idea, Cayley-Hamilton theorem. The Cayley-Hamilton theorem is, we all of us know the characteristic polynomial is such type determinant of lambda I minus a, which is actually written as lambda to the power n plus c n minus 1 times lambda to the power n minus 1 plus c n minus 2 times lambda to the power n minus 2 up to c naught. And here the plus sign, because I have considered lambda, determinant of lambda I minus a. This is the characteristic polynomial. And if we substitute here a, that means a to the power n plus c n minus 1 a to the power n minus 1 plus c n minus 2 a to the power n minus 2 up to a, then obviously this would be equal to always 0 matrix. And this is the Cayley-Hamilton theorem. Every square matrix satisfies is characteristic polynomial. As for example, consider the matrix A, then determinant of a lambda I 0 equal to 0 is the characteristic polynomial, and this would be lambda square minus 7 lambda plus 6 equal to 0. This is the characteristic polynomial of the matrix A, and these will satisfy the Cayley-Hamilton theorem. A square minus 7a plus 6i equal to 0. Let at first verify it. A square means 8 minus 14 minus 14 and put here this value a square minus 7a means 14 minus 14 minus 14 35 plus 6i means 6006, and calculate this value. This value would be always 0 matrix. That means A satisfies the characteristic polynomial, and this is the actual idea of Cayley-Hamilton theorem. Every matrix satisfies the characteristic polynomial, and since for this matrix it satisfies this characteristic equation, and obviously here the determinant of A is 6, which is not equal to 0. That means obviously inverse exists of this matrix, and by this equation we can find easily the inverse of this matrix. It is very easy to find inverse. Just multiply the equation both sides by A inverse times a square minus 7a plus 6i. Then this would be a minus 7i plus 6a inverse equal to 0, which is actually, notice this line, then we can write a inverse equal to 1 over 6 times 7i minus a. This is the inverse of this matrix A. Are you getting the expression? How we have to find inverse of the matrix by characteristic polynomial? Oh well. And this value would be, the value of 7i minus a would be 5 to 2 2. That means the value of A inverse would be 1 over 6 times 5 to 2 to find the a to the power, the power of a to the power 6. What would be the value of power of a to the power 6? From this expression we can tell obviously a square equal to 7a minus 6i. Okay? And if we multiply this equation by a, then a cube would be 7a square minus 6a. Now the value of, put the value of a square, then this would be 7a minus 6i minus 6a. Then this is equal to 49a minus 42i minus 6a, and which is actually equal to 43a minus 42i, and a4 would be 43a square minus 42a. Similar to before, just put the value of a square, 43, 7a minus 6i minus 42a, which is equal to 259a minus 6i. Okay? Similarly, a to the power 5 would be alpha a minus beta I type if we calculate, and then similarly a to the power 6 would be such type. Just compute the value. Are you getting? How we have to find the any power of A by characteristic polynomial? This is very easy. By characteristic polynomial to evaluate any power of A. Are you getting? If you know the characteristic polynomial, it will be very easy to find any power of A. Okay? Oh well. This is the actual importance of characteristic polynomial. If you know the characteristic polynomial, then you can easily evaluate power of any matrix. Also, you can easily evaluate the inverse of a matrix. If you know the characteristic polynomial. By characteristic polynomial, this is actually very easy to find. A to the power 100, a to the power 200, easily. Okay? Oh, we'll say the Cayley-Hamilton theorem of linear operator. Consider a polynomial fx equal to an x to the power n plus an minus 1 x to the power n minus 1 up to a2x square plus a1x plus a0. By Cayley-Hamilton theorem, obviously fa would be an a to the power n plus an minus 1 a to the power n plus a2 square plus a1a plus a0. But in linear operator, here A means just matrix, but in linear operator, ft would be an to the power n plus an minus 1 to the power n minus 1 plus up to a2t square plus a1a plus a0. Where t to the power n means obviously t composition t, this would be n times. Okay? And t square means obviously t composition t. Are you getting? OL. That means if f belongs to linear operator, that means if f be mapping from vector space to vector space, then obviously ft equal to 0 polynomial. Are you getting? OL. Let's see some example. At first, I will see the rotation matrix or rotation operator. Let's consider 90-degree rotation. Here, all vector be 90-degree rotation. At first, notice 90-degree rotation means cosine of 90 degree means 0, sine of 90 degree means 1, minus sine of 90 degree which means minus 1, and cosine of 90 degree means 0. Notice this matrix. Here I have considered 90-degree rotation. That means here every vector rotates 90 degree. Now I will see what is the eigenvalue and eigenvector of this matrix. Here the characteristic polynomial is such type would be minus lambda, minus 1, 1. That this is equal to 0 matrix. That means obviously lambda square plus 1 equal to 0. That implies lambda equal to plus minus I. Are you getting? From characteristic polynomial, how we will find the eigenvalue? This is the characteristic polynomial, and lambda equal to 1 and lambda equal to minus I be the eigenvalue. Okay? OL. And notice here the matrix be real, but I have got imaginary eigenvalue. That means from this idea I have learned any real matrix we can get the eigenvalue, and this may be either imaginary or real. Here noticed one interesting thing. This linear operator means rotation operator does not have a eigenvalue. Obviously this polynomial has a root, but this root not be member of real number, because here the polynomial is a real polynomial. For this, in group theory, I can tell R is not algebraically closed field because I have got one polynomial whose coefficient r belongs to real field, but zeros not be in the real number. So R is not algebraically closed. This is very important for any competitive exam. Notice here one interesting thing. Here the matrix is antisymmetric matrix because here P transpose equal to minus P. Okay. So there exists a nice theorem. Theorem is for a symmetric matrix always I will get real eigenvalues, and for these eigenvalues associated eigenvectors are always will be orthogonal. This is actually the theorem. Since here the antisymmetric matrix means P transpose equal to minus P, so here the eigenvalue not very real, eigenvalue are complex. This concept actually very important for not only competitive exam, for higher study also. Okay. Consider another matrix S equal to 0, 0, 1, 1, and here notice S transpose equal to S, and determinant of S minus lambda I equal to 0 means here by the calculating here the characteristic polynomial is lambda square minus 1 equal to 0. That means here the eigenvalue is plus minus 1. Notice since here the symmetric matrix, so eigenvalue are here real. Okay. Lambda equal to minus 1 I will get, this would be replaced by 1 1 1 1 x1 x2 0 0. That means x1 plus x2 equal to 0 from this expression. Also this expression x1 plus x2 is equal to 0. That means x1 equal to minus x2. That means eigenvector would be, since x1 equal to minus x2 here x2, that means this would be x2 times minus 1 1. That means for lambda equal to minus 1 the eigenvector would be such type. Okay. And lambda equal to 1, this would be minus 1 1 1 minus 1 x1 x2 equal to 0 0 matrix. That means from this expression minus x1 plus x2 equal to 0, that means x1 equal to x2. Also x1 minus x2 equal to 0, that means x1 equal to x2. Therefore the eigenvector, since x1 equal to x2, here also x1 equal to the x2, that means lambda equal to 1, the eigenvector would be 1 1. That means there exists two eigenvectors. For lambda equal to 1, the eigenvector are 1 1, and for lambda equal to minus 1, the eigenvector are minus 1 1. And notice here the eigenvector are mutually orthogonal to each other. I hope my all viewers have understood this theorem. For a symmetric matrix, always there exist real eigenvalues, and corresponding eigenvector are always be orthogonal. Today I will stop here. In my next video, I will discuss some example of eigenvalue and eigenvectors elaborately. Thank you so much. See you soon.